Hi everyone and welcome to this video. So, over the past few weeks, or a lot of weeks actually, I've been releasing videos about lithium ion cell capacity checker. And I've released the code, but I haven't really explained the code fully, at the end here. I've kind of bundled it together and just said there you go. So, I thought it'd be a good idea if I was to explain this code to you step by step as a summary so that you could just get a general idea. And for those who don't have much time, I suppose they could just skip straight to this video and get an idea of the code and what's involved in it. So let's get started. Include these two libraries, SPI because obviously we're using SPI, and Adafruit SSD 1306 because that's for my display. Without those things it just won't work. Then the define pin code. Then I've got over here the buzzer pin, the switch pin, the draining LED pin, the complete LED pin, standby pin, the MOSFET pin, battery voltage, preload voltage before the resistor, and post-load voltage for after the resistor. And I initialize this class thing here and get it going. Well, not class, I initialize this thing and get it going. Then const float load resistance. So this is the resistance of the resistors you have in place. So for me, it's 1.65 ohms. And obviously you'd put your amount of ohms there. Terminal resistance. So this is the resistance of the terminals of the cell holder. And comparatively to the wires and whatever else, these have a pretty high resistance. And it really matters because when you connect to the cell, you don't actually connect directly to the cell. You connect to the terminals of the cell holder. But don't forget that when you're draining, this is impacted. So you need to know the terminal resistance. Now, if you don't want to do that, then just write 0. Just put 0 in it. But if you want it to be accurate, then you need to actually measure the resistance of the terminals. And there are lots of ways of doing that, but I won't go into that. Anyway, internal reference adjust. Well, when you use the internal reference, you'll notice that it's probably not bang on. And you need to adjust it by a few millivolts. So that's what I do here. I've adjusted mine by 20 millivolts because it's 20 millivolts off. So there you go, I add 20 to it. Then we've got some variables here. MVPC means millivolts per count. And count is from 0 to 1023. So millivolts per count. But that sorts itself out later anyway. Some amperage, I won't go into that. The current menu is the menu that the user is currently looking at. The previous switch state is to do with detecting user input. Then we've got drain stop and drain start millis. That's to sort of keep a track of the current session, like how long it's been draining for. And then we've got some various other bits and pieces here. So we've got the drain sample interval, which is we take a sample every second. When it's draining, and update VCC interval, that's using the internal reference, and we poll the internal reference function every second. Now these things can be changed, but I'd advise that if you don't know the code, then don't change them, because some of these might influence other areas of the code. So we've got the limit for the current time, which is an unsigned long, and I don't expect that will ever need to overflow, because you probably wouldn't want to keep this on for days and days and days. So in the setup, we set up serial, and that's for diagnostics. If you don't want to use it or whatever, then you can comment it all out. So we begin displaying on the screen, clear the display, set all of the pin modes for all the pins, then we turn the standby pin on, which is blue, and then we set the text, and then this is the hello ... bit. It just refreshes, it just cleans it off every second or whatever it is and puts it on. Now, this really is probably too short. What I've noticed about the project is that it seems to need some time to warm up, and that seems to affect the ADC quality. So maybe if you leave this a bit longer, you'll probably get better results. And after a certain amount of time, when it warms up, it seems to be far more accurate. Okay, moving on. Let's go down here. So it says print hello. and this is this print hello that we've just gone over here, and it sets the cursor to the position on the screen. Then it prints the message, which is hello dot or hello dot 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 or whatever, then display, and then delay for 1 second. So it pauses the sketch or whatever for 1 second. And obviously that repeats 3 times and it goes to display menu 1. But let's look at this bit now. So it says standby pin on, and it does a digital write to the pin to say whether it's on or off, and this is of course the LED. And then if it's on, then set the other pins off. Then draining pin on is the same sort of thing, and completed pin on, that's also the same sort of thing, because remember I've got an RGB LED and there are 3 colours, so I need this 3 times. I could actually improve this, but and put over here the colour of the the colour of the LED which you want to switch, but whatever, that's good enough for now. And then turn load on. So turn load on, and then that's the parameter to say whether you want it on or off. So true means turn it on. So if true, or if you want to turn it on, then start the timer here, and then otherwise if it's not on, then it's off. So if it's off, then stop the timer. And this is in charge of starting and stopping the timer for the drain, or the load as I call it on here. So this draining pin on is of course the LED that we've just spoke about. So draining pin on, I think I remember rightly, that's the blue one. So, oh no, it's not the blue one actually, it's red. Yeah, this will be red. So, so turn the red LED on, which of course turns the other ones off. Then digital write MOSFET pin on, or off, depending on what the parameter is. So if it's turn load on, then it writes high to the MOSFET. If it's turn load off, it writes low to the MOSFET. And of course the MOSFET is the thing that acts as the switch in the draining loop, or the draining circuit. So then going over to display menu 1. Menu 1 is the screen that says insert cell now, press when ready. So it just obviously writes that, and that's pretty much all it does. And menu 2, it's the same thing but for menu 2. And in menu 2 it shows the voltage of course, which is all worked out here. And then press the start, etc. But menu 3 does this. It says cell under voltage, press the return. So it only goes to menu number 3 if the voltage is too low over here. So if you go to menu 2 and it says the voltage is too low and you press the user button, it will go to menu 3 if the voltage is too low, and if it's high or if it's okay, then it goes to the next menu, which is the draining menu, and it will start draining. Anyway, so display menu 4, obviously we clear it off, we set the number, we set the sum of the amperage to 0, which basically resets the draining section. Turn the load on. So turn load on basically changes the MOSFET, or changes the property of the MOSFET to turn it on. Turn load on turns the MOSFET on. Not only does it turn the MOSFET on, it also manages the time as well, which we just went over just a minute ago. And it prints this static content, because this is just when you first enter the menu, these functions are called here. So it prints this to the screen too. Menu 5 is the summary screen, and so we clear it off, we turn the load off, which of course turns the MOSFET off, and then we do some calculations. So total amount of milliseconds is the stop milliseconds, take away the start milliseconds, which leaves the duration of milliseconds. Then we convert that into seconds by dividing by 1,000, because there's 1,000 milliseconds in a second. Then we find out the total amount of minutes, and we don't have any decimals, it's just, in integer or whatever it's called. And then the duration in seconds then, but it's the amount of remaining seconds, if you like, with the minutes already taken off. So then we say that the completed pin is on, and by pin it should probably say LED pin or something like that. So we switch the LED pin on for that particular colour, and then that in turn turns the other 2 colours off if they're already on. Then we get the average amperage, and we do that by getting the running total, or the running sum, or whatever you want to call it, and divide it by the amount of seconds. And again, this isn't really the bomb-proof way of doing it, but it'll work for now. Well, it works perfectly well for now, as long as you don't start messing with it. So then we display the average, and we display it in milliamps, and obviously there's 1,000 milliamps in an amp, and that's why I've got this this bit here. Then I show the user-friendly amount of time, which is minutes and seconds. Obviously, the amount of milliseconds is not particularly useful to a human. Then I've got the duration in hours, and there are 3,600 seconds in an hour, so that's why I've got that there. And that's of course because we're trying to measure this in milliamp hour or amp hour. You know, not amp minute or amp second, it's amp hour. So we need to convert it into hours in order to be able to work that out. And then milliamp hour is the, you know, basically that multiplied by 1,000 to get it into milliamps. Because most cells are measured in milliamps, not really amps, unless they're big car batteries or whatever, which these lithium things generally aren't. So now this loop bit. So loop obviously repeats as fast as it can on the Arduino, which will probably be a nanosecond or whatever, I don't know. It's a very small amount of time from a human perspective anyway. So what does it do? It says if the current time is greater than the last VCC set plus the interval, then set the millivolts per count. And this business is all about the internal reference. So we're trying to find out the amount of, or the VCC of the Arduino, and we work it out every second or whatever it's set to. And this is to do with the accuracy of the ADC, because when we find out the VCC, we reset the amount of millivolts per count of the ADC in the hope that it gives us a little bit more accuracy. So we do that every second to see if the supply voltage has changed in any way, and therefore, you know, we need to change the amount of millivolts per count accordingly. So what's next? So we've done that. So check for user input here. So we find out the current state, like if the button's down or not, and then if the current state is low, in other words it's pressed, and the previous switch state, which remember rightly this could be like a couple of milliseconds ago, was high, then it's just been pressed. And that's what we want to know. We don't want to know if it's held or anything like that. We want to know when it's just been pressed. So if it's just been pressed, then we look at the menu which it was pressed on. So if it was pressed on menu 1, which is the insert cell thing, then if the voltage is greater than 3, we go to menu 2. If it's not greater than 3, we go to menu 3, which is the one that says, no, the voltage is too low. So if we're looking at menu 2, then what we do there is we'll skip straight to menu 4. So if we're on menu 2 and somebody presses the button, we go to menu 4, which is the drain screen. If we're on menu 3, which is the one that says your cell's no good, and somebody presses the button, then it goes back to menu 1, which is the thing which says insert your cell or something like that. Then if we're on menu 4, which is the main drain screen, and somebody presses the button, it will abandon it and go straight to the summary. And if you're on the summary and somebody presses the button, then it'll turn the standby pin on, which basically, resets it all back to menu 1 again. Which I'm actually thinking, I'm not sure if that's necessary. That standby pin may already be called in display menu 1, I'm not too sure, but it's only a small thing anyway. And it says the previous switch state equals whatever the switch state is now. That's just so that we keep on top of the switch states. And then what have we got here? So if we're on menu 4, which is the drain screen, and the current time is greater than the last sample plus the interval, then we need to sample the drain. So drain screen sample, it goes off and it samples the drain. So it takes a sample of different voltages so we can work out the amount of amperage, etc. And then we have a delay every 5 milliseconds at the end of the loop. So then going on to the drain screen sample, or sample the drain, or whatever you want to call it, we draw on a big black rectangle over all of the old values. And this is very lazy, it's not the proper way of doing it, but it's just the way I do it. It's good enough and it's easy. So then we do some calculation. So the battery voltage is the battery voltage pin multiplied by the amount of millivolts per count divided by 1,000. Okay, so that's the battery voltage, and then we display it there. Well, serial actually. Then we get the preload voltage, which is a similar sort of thing, and we get the post-load voltage, of course. So now we work out the voltage drop across the resistor, which is the preload, to take away the post-load, and we end up with the voltage drop. So because we know the voltage drop, and we know the resistance of the resistors, we can then work out amperage. It's pretty simple, just using Ohm's law. So then what we need to do is we need to try and work out from that the voltage drop across the terminals. And this can get a little bit complicated, so I'm not going to go into it too much, but the terminal voltage drop is basically the terminal resistance multiplied by the amperage, because if you know the resistance of something and you know the current, then you can work out the voltage drop. So then I output there via the serial console. Then if there's a ground difference, that also goes here, and this is the difference between the cathode voltage to the Arduino ground, and really this should be a constant float, which, yeah, I think I may change that. Yeah, const float. So I'll just put this at the top here. So let's put this right at the top. I'll have to remember to come back down here. Where is it? There. Const float, Control T, Control S. I'll have to re-upload this code now. Yeah, so that's the difference between the cathode and the Arduino ground. So where were we? Ground difference, we'll put it there. Yeah, I don't know why, but for me that's about 3 millivolts. Anyway, if you don't know or you don't want to work it out, just put 0. But you'll just lose a tiny bit of accuracy, that's all. So what's next? So battery voltage plus equals, which means add 2. The terminal drop multiplied by 2, because of course there are 2 terminals on the cell, and add the ground difference. And this just squeezes a tiny bit more accuracy out of the unit, or out of the project if you like. So then we get the sum amperage and add the current sample amperage to it, so that we can later on use it to find out the average, because you get the whole sum of all of the things and divide by the amount of samples, and that will get you the mean. So the current time 2, so we've got current time divided by 1,000 gives us the amount of seconds since the thing started. And then drain start millis 2 is obviously the drain start millis, so when it started draining, divided by 1,000, and that gives us the amount of time since the drain started. And then we print that out. I'm not sure why we print that. And then basically, because we're in the drain screen now, and this is repeating every second or whatever the sampling, if we've got the battery or the cell down to 3 volts or less, then we need to stop, because we don't want to damage it too much. So then at this point, we'll abandon the drain, which is menu 4, and we'll skip straight over to menu 5, which is the summary screen, and then we'll do a quick buzz. So this is buzz. Basically, it's just a for loop, which just does set the buzzer high for half a second, set it low for half a second, and it repeats 3 times, and that's the buzz function. And then set millivolts per count. This is not really an easy one to go through. I didn't write this code, I've copied it, so I'm not going to explain it. But essentially what it does is it does some calculations to get the amount of it gets the VCC, basically the supply voltage to your Arduino. It gets it via this internal reference, which basically, if your supply voltage VCC is 5 volts, then this internal reference will be exactly 1.1 volts. So using that, you can play about with it to work out, what your supply voltage is. And there's a few calculations that I've done here which were not copied, and that's basically device voltage equals the result of this divided by 1,000 and I print it via serial there. And this is the important thing, knowing the amount of millivolts per count, because this is what defines the accuracy of the ADC basically. So millivolts per count is the result, and that means the supply voltage divided by 1024, and then we're outputting the amount of millivolts per ADC count. And that is the whole lot of code explained in a few minutes. So I hope that's sufficient, and as usual, thank you for watching. If you've got any questions or anything like that, feel free to leave a comment and I'll try and sort it out for you. Thanks again. Bye.